Hey, thank you very much, Annette, and welcome to all. And thank you for giving me the opportunity to introduce this forum on frontiers of food production and food waste recycling. At previous occasions, I had the possibility to say a few words about BrIAS and how it came along, etc. I will tell you a little more this afternoon. In fact, the origin of the project comes from the previous rector of this university, Didier Vivier, who in 2017, at the occasions of discussions concerning the future role of former military barracks, which are within walking distance of this campus, very nice listed buildings that have to be renovated. And the question was, how will those be used? And then the university said, both ULB and VUB, well, let's make use of those buildings. And Didier Vivier said, Brussels did not have an Institute of Advanced Studies, despite the number of university labs of very high quality here in Brussels. So why not create a Brussels Institute for Advanced Studies in the framework of the U-Square project, which are those former military barracks, and a collaboration between the two sister universities. Then, maybe just to recall something about the universities and the situation in Brussels. When you look at the number of students of both universities, plus then the hospitals of both, there are more than 60,000 students now at both universities, which in fact makes Brussels the largest university town in Belgium. And together with those hospitals, there are more than 16,000 members of personnel. So from the economic and cultural point of view and educational point of view, this is of course extremely important. We don't always realize, those who know the Belgians know that we are a little too, well, we don't show that we know a lot of things. In fact, at those universities here, we had 6 Nobel laureates, 2 Abel laureates. The Abel Prize has been created by the King of Norway to give a prize to mathematicians, because you may know that there is no Nobel Prize for mathematics. And 2 field medals, which are also similar to the Nobel Prize for mathematics. And so out of those 6 Nobels and 2 Abels and 2 fields were either professor or alumni of those universities. This was a little publicity for ULB and VUB, right? So then in June 2018, the rector of VUB, Caroline Pauwels, and of ULB, Yvon Angler, respectively asked Serge Joumin for ULB and myself if we could jointly develop the action plan for the creation of the Institute for Advanced Studies as a joint initiative and located from 2024 on in the former barracks. And I can tell you this was, and it still is, quite a challenge, but a very interesting one. This is the location where it will be, where you will be as fellows housed and be able to work for several months from 2024 on. The main sources of inspiration we use to build the concept. Someone clearly has a microphone on. I told you previously about the inspiration we got from the Solvay conferences, and from the Princeton Institute for Advanced Studies, where people such as Einstein and Oppenheimer, etc., resided and worked. But let me now say a few things about other ones that really inspired us. For example, colleague in Berlin. I'm not going to read it, just a few ideas. So optimal working conditions, of course, in order to give unforeseeable stimulation and creative provocation. An intellectually heterogeneous atmosphere, which points to transdisciplinary approaches. And productive friction, that is, people don't have to agree always. When you put an artist together with a scientist, they have totally different approaches for the same problem. And this may again be a way to have disruptive new ideas. So unexpected innovation. This is from the mission colleague in Berlin. Nias in Amsterdam says, driven by curiosity and cross-discipline collaboration. So you see always interdisciplinarity will come back. Breaking down cross-discipline barriers. We have to build bridges across disciplines. In Marseille, it says scientists from all disciplines, artists and social actors, thinkers and makers, not exclusively academic, and it's the risky ambition to confront necessary utopias. So it's really something which is not strictly project bound, but much wider, with, of course, a social engagement of knowledge. And this one is I like very much, the Santa Fe Institute. It's always pushing creativity to its practical limits. We always call the high risk of failure, we too have to admit this. But above all, we have more fun than should be legal. We are absolutely relentless in the hammering down boundaries created by academic disciplines and by institutional structures. So remove the walls and create bridges. We are beyond relentless, sorry for my pronunciation, in seeking out the best people, etc. We will give space and resources. And then occasionally we find out that an invited guest is insane, and this generally cheers us all up. We know we are on the right track. So those elements were really inspiration for the mission statement, in which we repeat exactly the same concepts: interdisciplinarity or transdisciplinarity, the best researchers at international level, working towards a sustainable world, strengthen mutual as well and worldwide collaborations between the university, between researchers, stimulate interaction between science and other instances of creativity such as arts and design, and contribute to the sustainable future and the prestige of the Brussels region. And we do this by offering an environment as an incubator of ideas, no philosophical or political restrictions at all, total academic freedom, cross-fertilization, and breaking down the walls of ignorance and dogmatism without taboos or prejudice. This is our vision. Now, you have seen that there are other institutes of advanced studies in the world and in Europe. There was none until recently in Belgium. Now there are two. We were created, as you have seen, in 2018, and this year, last year, by the end of last year, one was created in Leuven. Now, we have a few specific niches which are typical for, I would say, the DNA of those universities. That is potentially controversial subjects with an important societal impact. We want to welcome researchers who are in danger. When we wrote the text, we thought more about Turkey and those places, Today, unfortunately, it's more Ukraine which is in the news. And then we specifically also want collaborations with institutions and researchers in countries such as in the south of the world, where society faces critical challenges with respect to sustainability and where they may have less financial and other means to do their research. Transdisciplinarity, when you look at the program of today, it's on Earth and space, applications, you know the titles, for example, space, and of course the translation of those techniques and of those insights to applications on our planet. So it's a very promising transdisciplinary program, and I really look forward to hear your presentations. Thank you very much.
Thank you very much, Frank. I'll quickly set up the next presentation and have a little transitionary statement for you. A moment. Okay. So here we are. Are we sharing? Yes. Okay. Now, we welcome you all to our forum on new frontiers of food production and food waste upcycling, a topic that is timely and relevant for our society and world as we confront challenges of reducing food waste to improving food quality for all who live on our planet. With the talks by our speakers today, we will be able to take a journey on scientific discoveries and technological breakthroughs that will allow us to address these challenges, from upcycling food waste to improve the soil beneath our feet, and one day grow food and bake bread amongst the stars. So, and with that, I would like to invite Professor Canella to take the floor to introduce our first speaker of today.
Many thanks, Annette. So it's my pleasure to invite the first speaker of today. That's Stijn Roovers, that represents today Permafungi, which is it was a spin-off. Now it's an established company in Brussels that is taking up the recycling of many waste resources into edible food and much more. So Stijn will introduce us to this new reality, just let's say created here in Brussels. So Stijn just graduated in KU Leuven. I just learned about it from sociological sciences. So once more, he's not a boring scientist. That's for you. And then he can really give us a different angle of how to translate technology into something useful. So he has been much involved in works in NGOs and so on. You were speaking about the south part of the world. So he was in Bolivia before, and then helping in translating and helping enabling this technology for the help of the society. Then he came back to Belgium, where he started working in Brussels, Molenbeek. Once again, this kind of NGOs that helps in social activities within Brussels region. And then later on, he also volunteered before getting a position in Permafungi. So once again, to the young people down there, you see. So motivation brings you to the position that you want, or you really want. So you volunteer for that. And today he is representing as a CEO the Permafungi company. So without further ado, I leave the floor to Stijn, and enjoy.
Thank you for the introduction. Thank you for having me. So I'll probably be giving you the more economic, I think, social economic point of view than scientific, but really interesting, I can assure you. So let's start with this first slide. So Permafungi actually Our main objective, our big objective, is to make the transition to a circular economy. This circularity, it's our ADN. It's really central. It's the core of what we do. And we started by doing this, as you see on the picture, by producing oyster mushrooms on coffee grinds, on coffee waste. But that's not all. We do much more now after 10 years. And personally, this idea came to me by reading The Blue Economy of Günter Pauli. It's someone from Antwerp, the CEO of Ecover. And he put it actually, interestingly, the expensive green economy versus the linear waste economy. And he suggests we need a blue economy. And this blue economy, it's based on natural systems, but it can be locally introduced. We don't need it to be produced on the other side of the world. We can enable this kind of mechanisms in a local way, and we leave local entrepreneurs to do it. And he gives the example of a Colombian cooperative, and that discovered that their coffee waste, and we're not talking about the coffee grinds, but the coffee waste in the process of making the coffee beans, that it can be used to produce shiitake mushrooms, which after the mycelium of the shiitake has been introduced in the coffee waste, can be fed to animals. So actually this is a good example of this circular economy, the circular thinking. So after this example, a lot of entrepreneurs started with, mostly in bigger cities in Europe, started implementing this idea. And so did we. Actually, we believe, we go a bit further, we believe that fungi can save the world. And this phrase is not something that we invented, it's a phrase of Paul Stamets, the mushroom and fungi guru, let's say. And he suggests, he presented 6 cases on a TED Talk in which he is convinced that fungi can save the world. It's very interesting. So we also convinced that fungi can save the world. So we want to collaborate with fungi to create healthier cities. So it's not only about these mushrooms, it's the fungi. These are different kinds of things, if you know. So we collaborate with the fungi to make healthier cities. We use this natural system, this natural thing that exists to create healthier cities that are mostly, let's say, human-oriented ecosystems. Why do we want to do that? To contribute to urban resilience. So this urban resilience is important. So you're all familiar with the term resilience. That's the capability of a system to absorb shocks without structurally changing the properties of the system. This is what we want to do. We're completely invaded with shocks, more and more actually, in different kind of ways. So how can we face up to these challenges, not only by producing food locally and recycling waste locally, but also by using these other properties of fungi, in this case, to make things happen. How do we do that? Once again, by accelerating the circular economy versus the linear economy. We're convinced that this model is the model of the future. And so what concretely are we doing? We're impacting society in multiple ways. So the first and the most important one is producing food that is healthy, nutritious, delicious, locally produced, super fresh, which is already kind of special. If you see that, for example, the most of the oyster mushroom that you see in the shops come from Holland, which is quite okay, but also from Poland. So you all have these transport hours that you have to take into account, which means you lose quality of the product. We harvest the mushroom in the morning, in the afternoon it can be in the store, so we have a super fresh product. We valorize urban waste, the coffee grinds, I will tell you more about it, and we use vacant spaces. Vacant spaces is also very interesting because there is a social profit organization, Toestand. They calculated that in Brussels 6.5 billion square meters is left vacant. This is the surface of the municipality of Elsene. So actually we can fill a 20th municipality in Brussels with all these this vacant space. So it's a huge problem, but it's also a huge potential for this kind of productive activities. We also want to create a skilled workforce, and we do this by having a link with Actiris. Actiris is responsible for market labor insertion in Brussels. So people that have a difficult, persons that have difficult access to labor market, they come to us, they work with us 6 months, we train them, and then they have a better positions to start on the labor market. And it's a very conscious choice we made. It's not the most easy one, but it's creating impact. Raising awareness in the population. So this is also very important. We're in the seat of Tour and Taxi in the caves of Tour and Taxi, 12,000 square meters, but it's in the heart of Molenbeek. Molenbeek, which always comes up when there's something wrong in general, unfortunately. We talk about Molenbeek when we talk about the croissant pauvre, where there's a high unemployment rates for young people. So if we can explain to these young people what circular economy means, make it tangible, make it something that they could understand, then we can also impact their way of thinking and their way of seeing society in a whole. Last but not least, the constant innovation and implementing new products and ideas. And this we will come back to you. That's why we changed from mushrooms to the fungi part. So we started in 2013 with 3 main activities. So actually it's a bioengineer and a social entrepreneur that came together. They made a trip to Thailand and they saw, oh yeah, in Thailand they're also doing this thing. We want to start it in Brussels. Okay, let's do it. So we have 3 main activities: eat, grow, and learn. Eat is the production of the mushrooms, oyster mushrooms, in a circular manner by using the coffee waste in our flagship location in Tour and Taxi. The grow is to encourage others to grow these mushrooms at home and recycle the waste at home, because also there we can make an impact. If we are able to change the way we look at waste in the living room, then we have a bigger impact than we do it outside. Say, if we look at this in a daily way, we can really be able to change this kind of perception of how we look at waste. So of course we do this by selling and proposing kits and methods to do this. And the learn is the knowledge sharing, it's visits, workshops, and professional trainings for entrepreneurs. Nature itself inspired our model, and it all starts, let's say, with the coffee grains. Let's do a test. Who likes a cup of coffee in the morning here in this room? Please raise your hand. Yes, like always, it's the majority, which is good news. I can do the same for the tea drinking people. We can also use your tea waste. But there are some interesting facts about the coffee grains. The first one is that if we look at the whole cycle of the coffee production, so from the beginning until the end, actually what we end up with, it's a liquid. It's not even the vast compound of the coffee waste of the coffee. We end up with a liquid, and this liquid is 0.2% of the energetic potential of the whole coffee, or the whole coffee bean from the beginning. So the biggest part we throw away. Actually, it's a big change. We produce coffee on the other side of the world. We have a huge impact, and we end up with the smallest, super small part of it, drinking and consuming. It's the biggest part. We throw it away, and throw it away. It's relative because it's biomass. We can compost it. But the biggest part, and especially in the cities, it's not being processed as organic waste. It ends up in the domestic waste as a domestic waste product. So it also ends up in the incinerated, being incinerated, and so there's a direct link also to make with greenhouse gas emissions, climate change, of course, in a reduced way. But the second thing that we found out is that on average a Belgian person drinks about 5 kilograms of dry coffee waste a year. That's a dry part. Of course, if it's wet part, you can add 1 or 2 kilo. So it means that if you look at only Belgium, we end up with 60 billion kilograms of coffee waste that has to go somewhere, of course. So again, it can be a huge problem, but for us, it's probably a huge potential. It means that it's abundantly available, which is good for us, of course. So this is the most important thing about the coffee grain. We use it as a substrate. It has a high energetic potential. It's abundantly available. And we have a greenhouse gas emission problem. Yeah, no problem. So which makes us, if we look at the whole chain, it makes us one actor. It makes us one little chain if you look at the whole process. We can't change the world wanting to do everything. We want to specialize and gain expertise on what we're good at. That's what we try to do in Permafungi. So we need other partners to deliver on the input side and to deliver on the output side, let's say. So that's, let's say, the second part of the circular way of thinking. It's making connections. It's putting the dots together, putting the pieces of the puzzle together, creating an impact. So we have these coffee grains. We have this substrate. It's not only coffee. We add another product to make create volume and to permit that the oxygen can create volume, so the oxygen can reach the fungi, so it can grow. But we have a yield of, let's say, 20% on average. So this means we have like 10 kilogram of substrate leads to 2 kilograms of mushrooms. We produce 1 ton of oyster mushrooms a month. So we end up with 5 tons of substrate. Oh, is this a different waste product? It is, but again, it can be converted in something interesting, namely compost. It's an excellent compost of fungi. We have the straw in the beginning, or another organic waste stream that creates volume, and we have the coffee waste that you can put it on your compost. You can use it in the production of greens and vegetables. But putting the two together and introducing the mycelium creates even a better compost. So this is being used, it's being recycled in an urban farm here in Brussels, Ferm, which uses it to grow vegetables and so on. So that's our first circularity, let's say. That's our first circular model. We tried to go further. 2 years ago, we wanted to create endives, chicon, witlof, because we were in the basement. We had all the conditions were there, so we thought, why not? We have a substrate left. Maybe we can grow the chicons on the endives on this substrate, and that's something which we started. We are let's say we're a small company. We try to respect the low-tech properties also. You can do it low-tech, you can make high-tech. We chose for low-tech. And so this translates into a business, let's say an economic way of thinking that we call lean development. The lean development means you're going to put to the point your protocols before advancing. So you go slow but steady. You're sure of the steps you're going to take, but you go slow, you don't need a lot of capital. And that's what a good model to start with the endives. So we started it, but after 2 years, we ended up doing something that was completely disconnected because there were a lot of processes going. We couldn't use a substrate, so we added other materials. So, and in the end, we had an aquaculture actually, but a water culture because it was rotting and so on. So we started something that we couldn't bring to an end. So we stopped. Yeah, everyone can make mistakes. But you have to be able to say to stop if it doesn't work. So now we're starting someone else. We're starting something else. We're starting the myco-materials part, making composites. I will tell you more about it later on. But the most important thing is this, again, this circularity, this circular model which enables us to look at things differently, at waste streams differently, and so on. I'm just going to give you some numbers. So we're 2,000 square meters valorized. We have like 10,000 visits in 5 years. We produced 8 tons of endives, which is not bad, but we had to stop it. We do 30,000 kilometers by cargo bike in Brussels a year. We have 10 jobs valorized. We have 150 ton of organic waste valorized a year. And interestingly, I would say this is also, we can make the link with the CO2, let's say, or in general the greenhouse gas emission not being dispelled. And this is interesting because it shows the direct impact, and it shows the impact in numbers by using the life cycle analysis we did. And this is what makes it the thing that we're doing tangible. It makes it concrete. It makes us having a certain impact that we can calculate also, that we can put in numbers. These are rough calculations, to be honest. So for us, let's say the future is looking bright. Sometimes it's looking more brighter than other days, but we identified two main areas of growth. And the first one is the perma cities. And actually it's based on this network model. You have to choose your battles, and our battle is at, let's say, the end part of the, if you took a look at the coffee grain, we end up with the waste product. And actually it started from a lot of demands we got of universities in Antwerp, for example, but also public and private actors that came to us with the demand, look, I've got some coffee waste here, we want to change something in our business. We have coffee waste, can you do something with this? Can you use this to produce the mushrooms? And it's interesting because it's a small starting point of people who are changing their way of thinking. And actually this is something to start with, and what we are doing, we try to go further. Instead of sending us the coffee waste from the other side of the country to Brussels, why not trying to valorize this coffee waste locally and produce local mushrooms? So we tried to, let's say, make a business, make not a profit, but we tried, instead of making Permafungi a multinational that will conquer the world by producing mushrooms in different cities. That's not, I don't like this this idea. It won't be true, never. But we will be able to enable our own expertise, which is low tech, which is really flexible, and put it into practice and accompany other actors, private and public actors, to locally valorize coffee waste or other waste streams and produce local food in urban context. So this is generating impact on a different way, but it can be an economic model, it can be a profitable model, it can be an interesting business model. And the third one, we started Permateria. We still have to think about more sexy names, but for the moment it's Permateria. And that's actually the next circular cycle that we're going to make. So we have our mushroom cycle, we have the substrate we call champost being reintroduced in the production of vegetables and so on. But what if we can use it for other things? We tried the endives. We have 5 tons of champost a month. This is a huge potential. So we started off doing tests, reintroducing another type of fungi into this material, incubating it 1 and 2 times in a mold, so in a certain form, and not going to the third phase of fructification, but stopping it and drying it. So actually trying to create materials. We started 5 years ago with these lampshades, you see, and this was like an interesting product. It was the eco-design market, so it's quite a niche. But recently we started doing tests to introduce products in the packaging and in the insulation market. Packaging is really interesting, and it's a huge potential if we could be able to replace styrofoam, for example. Styrofoam, actually, it's also an observed product because it has a lifespan of maybe half an hour to transport furniture from point A to point B, but it needs 500 years to degrade. So it's completely ridiculous if you think about it. It takes huge volumes. It can only be treated as domestic, let's say, domestic waste, as industrial waste. So what if we are able to replace this material by a biodegradable alternative that needs 3 weeks instead of 500 years, and you can just throw it on the compost bin. So that's one sector we're trying to reach, and the other one is the insulation sector, because the properties of this material are amazing. We have, in general, it's water repellent, it's fire retardant, it's very light, it has very good thermic and acoustic qualities. So if you look at the lambda values and so on, it's really interesting. It's here at this university, at the VUB, with Professor Peters, I think, Elise Elzacker, who 2 years ago produced a PhD about different substrate, different mycelia to make composites. And this was our inspiration also to launch tests in our own laboratorium for this kind of materials. That's what we're doing now, and it's thrilling because tomorrow we are going to install the first, let's say, acoustic wall in the city FAPS here in Belgium, and that will probably be the first wall being installed with this myco-materials, with this insulation panel. So it's for acoustic isolation in a media lab. So it's really interesting, it's quite thrilling. Of course, there are always challenges, and this is a picture of the caves, let's say the basement of Tour and Taxi. And you see clearly that we're not in a laboratory setting. So we have to deal with the limits that this infrastructure imposes. And this, for example, one of the concrete translation of these limits is that we can only produce oyster mushrooms because it's a dominant and quite aggressive mushroom. And the tests we did on, for example, shiitake, king oyster, enoki, and so on, they failed because we couldn't control the conditions. The biggest enemy of a mushroom producer is contamination by outer spores, bacteria, and so on. So this is clearly the vacant space. We have to put it in the balance between the other type that we can produce, the other type of mushrooms we can produce. We're using these buddhas, these plastic bags, and that's quite a problem for us because we're introducing plastic into the cycle. It's recycled plastic, but we did a lot of tests with other materials. For example, with reusable buckets, it works, but we need a full-time person to clean it, to store it, and so on. So as a business model, it's quite hard to realize. We also did tests with biodegradable bags, but of course the fungi recognizes the bag as something interesting to feed on. So we found half of the bag on the ground. So we have to go digger plastic, but that it's more expensive. So it's all things that we have to balance. And the other thing that we noticed is also the market position. What we need now for the moment is, let's say, the early adopters. We're aiming the big companies. We're aiming the big businesses. For the mushroom, we're talking about the Sodexos, Compass, Carrefours, and so on of this world, because there is where we can make the impact. But they're all very engaged and so on until we talk about the numbers. And of course, we are offering a product that is built, that's made out of waste, and that is super fresh. And we want this product to reflect the real price. And we don't want to participate in this race to the bottom, growing bigger to produce at a lower price and so on. So it's for the moment, we notice that the market is not there yet, but we try to, and that's the last challenge, we try to balance the idealism with which Permafungi was created with the necessity of being able to pay a salary at the end of the month. So to be able to do this, it's a constant choice between let's say the profitability that you want to achieve with the company and the idealistic way of working which we started, but we still, I think for the moment, we're still keeping up with let's say the heart at the right place of the people working with Permafungi. So that's what I wanted to tell you.
now we have some questions also from the online people, so if they can hear me. So normally we allow people to write their question on the chat, and then usually Annette helps us in reading it to check if there's any question. The audience first. Please.
Thinking about the economics, when you were saying people in other cities and things, can you work that on a sort of franchise basis, so pay you money for that sort of thing and use all your logos?
Yes, yeah, it's so which model which economic model you can use in using this Perma-cities model. Actually, the last year we worked with Accenture on identifying potential models. We ended up with 12 potential models that could be used. Of course, 12 models, it's too big, and one of these models was the franchise model. But of these 12 models, for us, we defined 3 that can work for us. One of these models is the traditional, let's say, reproduce for you model. So you say, for example, a Carrefour. We make a contract with Carrefour, and they buy a fixed amount with a fixed price for a fixed period of time of mushrooms. And we run the factory, we build the factory, but it's for their business actually. That's the B2B, one B2B model. The second one is a joint venture. We do it together. We put in the capital, we put in the workforce and so on. So that's the most comprehensive model, let's say. And the third model, it's a model that complements these 2 models. It's the, let's say, the consultants model. We make it happen with you. We give you the advice on your size about what we can do. And this can start from, for example, one professional training of 2 days, and it can end up with us building the mushroom factory, and then let's say giving it to the partner and being able to run it. So this is a flexible option that complements the 2 others, or that is possible. It makes it possible to respond to concrete questions of concrete actors. But the franchise model is a possibility, but not for us, not for us for the moment. So we're going for these. We aim at the joint venture model. If this doesn't work out, we go for the fixed supply, fixed period of time, and we complement with the consultants model.
Mark, please.
Yeah, I'd like to mention it very much. I think it's very nice to do these things. There's a lot of competition, I think, because I've there's quite a few companies that do these kind of things. I was wondering, because you say you add to the circularity in the economy, but it still looks fairly linear, what you're doing, because you use a waste product and you create something, but to really go to make it circular, you have to put things back into where the coffee is coming from. It could be Brazil or India or Sumatra or wherever it's coming from. Have you thought about that? Are you going to really make it circular?
Well, let's.
Stijn, I would just like to repeat the question for the people online.
Yeah,
so the question from Professor Mark Hart was, I mean, if it's a true circular economy model, would it be more wise to include in the circularity the origin of where the coffee beans come from? So going back to the original place in South America or Africa where these beans come from.
Yeah,
Stijn, please.
Well, I think I don't agree with not being circular, because we are reintroducing it, but we're just not reintroducing it in the countries of origin. That's true, but we're reintroducing it, a waste product being locally they use it for local production. So in a way, it's closing a loop. And I think once again we are only one part in the whole chain of different actors, and I think it's not our expertise to close the gap, let's say, with the global south, and we need other actors probably to be able to do it, and then we look at the non-profit, academic and so on, other institutions, but being able to close this gap would be definitely a great fund. It would be the let's say the whole circular loop being able to close, but I think that we are by recycling and valorizing the waste locally, we are closing a loop locally also, but maybe not the loop of the original coffee bean, but that is probably not our battle. Let's say we're probably looking a more local way of being able to function in a circular way. But I understand the point.
But you could ship the styrofoam made by Permafungi.
Yeah, for example. Yeah.
So
it's even better to have a Brazilian factory launched actually. But, yeah.
If in case you have to ship something down there, you can ship it by using this, and maybe only one-way trip, and then buy it locally.
Yeah. Yeah. True. Good idea. Yeah. Yeah.
I think we have a question from online people.
Yes. We have one question from Professor Seth Murray from Texas, and he has a comment and a question. Having grown some different oyster varieties, there is diversity for growth and end phenotype. I might have missed it, but have you screened many varieties, and are there any efforts to breed better varieties for your purposes?
Yeah, thank you for the question. Actually, it's also a choice we made ourselves. We're not producing our own varieties. As you saw in the picture, we don't have the conditions to produce our own mycelium, unfortunately, because this would permit us to experiment with which varieties grow in the concrete circumstances that we operate in. So we depend on the producers of mycelium, and we have one in Ghent, in Denze. It's Mycelia. And we asked them we use the 5 varieties of oyster mushrooms they have, and we asked them also to test other varieties. So this is we have a very nice relation with them also. But so us as Permafungi testing or producing our own mycelium, it's not something we're doing for the moment, but it can be an option. Instead, we chose to change our model actually. Instead of producing our own mycelium and depending on this, we defined these other changes that we could use to make a profitable business actually.
Paul, please.
Yeah, I have a curiosity question. How do you collect the coffee ground, and does that cost or not?
Yeah. So the question is, how do we collect the coffee grounds? We do this in 2 ways. So we have a deal with Le Pain Quotidien. I don't know if you know them. And it's like a reverse logistics. So actually they are responsible for they collect from all the restaurants, they collect the coffee waste. They bring it together in one big truck. They bring it to us in tour and taxi, and they leave with oyster mushrooms. So that's the idea of the reverse logistics. That's one way, and the other one is that we use our cargo bike every 2 days we drive out with the cargo bike. We pass by 8 esquisse bars, and there we collect the other part to complete both of them. And that's where we get for the moment our coffee waste. And our biggest clients, for example, for the moment are the local shops, shops here in Brussels on the one hand, and Tarte Françoise, I don't know if you know them. On the other hand, they buy like 500-600 kilograms of mushroom a month. So these are the kind of clients we try to target. Also the bigger clients, because the conditions have to be quite. We now have a big machine. We pasteurize actually once we receive the coffee waste, we pasteurize it again. In the beginning, we didn't do this. And there we had to trust on the water being poured when you put your coffee, the coffee waste being sterile, and we had to collect the coffee waste within 48 hours to be able to use it immediately. So using this trusting on the product that was being delivered, not containing too much spores and bacteria. So Yeah.
Just a final comment from Stijn. He thanks you for the answer, but also is encouraging to look also into other varieties, because this might help solve problems with the part of breaking down the plastic containers and bags.
Okay.
So that maybe
Great.
variety can help in this way.
Thank you. Okay.
You say that your company is like 10 years old, it's not that young, but not that old too. I'm wondering if like your goal is only to develop the fungi process, because like in plastic bags you have some issues to address. You have like a research and development department, you go to universities, you think you have a department if you don't have, how's the company about this?
Yes, so we're a small company. We have 5 people, 5 persons working. So we're one big department, I think, not a lot of departments. And recently we recruited a scientific researcher. So up until now, we didn't have a background we didn't have a scientific background. We have an entrepreneurial background and so on. So this also has kinds of limits. So now with the scientific researcher, we are able to do tests that go more into detail about what's possible, but it's more oriented on the composite side than the food production side. But it's actually true what you say, that discovering also that the VLB, the ULB have this kind of facilities and investigation, it would be really, really great for us to make the link. So we're very, very keen on
I think it sounds like us applying for a job. So.
Yeah.
So good. So you can talk with Stijn probably helping development. So if there's no other question, we'll leave the floor for the next speaker.
Yeah.
Thanks a lot again, Stijn. And then,
Thank you very much. Thank you very much, Stijn. I'll be setting up the next presentation, and soon we will hear from Frank de Koning, who will introduce our next speaker.
Thank you. So the next presentation concerns Melissa, a brief history. And the speaker, Max Merget, and he has a co-author, Christophe Lasseur from ESA ESTEC. Max will explain everything about it. It's a real personal privilege to be able to introduce a friend, Max. Max studied chemistry here at this university, Université Libre de Bruxelles, and he made his PhD in microbiology, and eventually he would become professor here and teach genetics. In the meantime, he joined the Belgian Nuclear Research Center, SCKCEN, where he was the head of the lab on genetics and microbiology. And concerning the subject of today, he is the father, I would say, of Melissa. There is a saying, success has many fathers and failure is an orphan. And for me, Max, you are really the father of Melissa. Probably you will say that you were not alone, because indeed you had to create a team. So not only you are the scientific father, but also you made a very coherent and excellent international team. And this is really wonderful. Max, you have the floor.
Thanks so much for the welcome.
You have to stand in front of the computer because there is a camera. Yeah, no, that's okay.
So you can understand me so? Ah, merci, thank you. So I have to be confirmed. Yeah. Melissa, brief history. Table of content. I mean, Melissa, it is for micro-ecological life support system alternative. Bon, it's a strange acronym, but Melissa, it is easy to retain. But life support system into space. A bit of history, I will describe this table of contents. Bit of history, project organization, science engineering, flight experiments, terrestrial application, the pump project on which I am responsible, events towards the conclusions. It is a presentation with Christophe Lasser from the European Space Agency. And European Space Agency, you see all the countries who are members of the ESA, including Canada, far from Europe, but Canada prefers to work with Europa instead of America. And so it is, you will see many countries. Next slide, a bit of history, the early beginnings. It was an intuition of Claude Chipot from Matra-Espace Airbus. Airbus was interested in space, and he said, tiens, would it be possible to put alga, eatable material to the space? That was in 87. He has the opportunity to make a flight with in a Chinese rocket where you put some microalgae grown in CNRS. And that was the very first experiment, just a Chinese flight, in 87. Later, Claude Chipot visited our institute to visit somebody interested in the skeleton and the resistance to man in the space. And I met him accidentally. I went to the library, he came from the toilet. I am looking for this person. What is your job? What are you doing? Voilà. My specialty is environmental microbiology. Oh, that is interesting. A way we try to put microbes in the space to recycle waste. Oh, yeah. It could be of interest. And so that was the beginning of a nice story. A fortuitous encounter, and I put him in contact with a specialist of environmental microbiology, Willy Verstraat. So that was the birth of the Melissa concept with Willy Verstraat in Ghent. And so combination of different labs, including ELSA ESTEC. Life support system Melissa, a microorganism built for CLSS development, control ecological life support system. 1988. So next Melissa actors. University of Clermont-Auvergne. Gilles Dulsap, Jean-François Cornet, these people are really the specialists of modelization, and they remain involved in modelization of all the Melissa concepts. 1988, 1989, Christophe Lasser came in stage. First, intervention of Lisa Estek et plus Clermont. Next new partner, Canada, University Gulf, involving plants. And finally, ESA, described this own vision. ESA development, life support technology, achievement and future priorities. It has an important construction where the ESA defined the future publishing Acta Astronautica. In 2001. And next step, important interest from Spain. Spain, Barcelona, and Barcelona, like the future place of the Melissa Loop, where the Melissa Loop was constructed with a lot of technology and connection and so on. And also the Swiss competitive and developing all the context linked to industrial ecology, Soren Ekman. And one of students of Soren Ekman is now defending an important PhD thesis. This is available on the website of the Melissa Foundation. Better times. I have to mention here the collaboration with Russia. And very important collaboration for me. We had, as you can see, 12 collaborative publications with Russian colleagues from Moscow, from Krasnoyarsk. I went to Krasnoyarsk, the middle of Siberia, where we had a formidable, fantastic welcome. And also we had the opportunity to make many experiments, many flights in Baikonur, where we had contacts. And as you see, many of the experiments were coordinated by Natalie. We had excellent memories of these experiments. So, Natalie is truly one of the best specialists for the comparison of bacteria between space and ground. So, some example of the publications we had with the family Tikhonov in Krasnoyarsk. Belgian labs came on stage. Mol, Mons, Antwerp. Is it possible to have because the top of the chemistry, the Instituto, some.
Yeah, there is.
Yeah.
There is more, I don't.
I think it's a cursor that,
Yeah.
the cursor maybe up. Sometimes.
Sometimes I can. Oops. Maybe I can move this way.
Or you can.
Up. Sure. I think.
Thank you so much. So Belgium come on stage, Jugend, Vito University in Mol, University of Mons, and later University of Antwerp. So that's different aspects, different publication from this collaboration. You see the intense and systematic collaboration between all the labs inside the Melissa community. It will be linked to
Just a moment. I'll just bring it down. Let's try to. I think we're still sharing. Okay, let's bring it back.
Voilà. The compartments and main steps of the Melissa loop. So maybe yes. Melissa loop, it is a loop. And the loop begins first by the treatment of a waste. And this is the transformation of the waste in food. In food that could be used by the crew into space. And so the waste has to be anaerobically treated.
In front of the micro. Yeah.
Always a little bit cinema with Maxime, okay. Oh. And the waste has to be treated anaerobically, processed to avoid all the contaminants at high temperature with thermophiles bacteria. It is a guarantee we have to have not pathogens with the treatment of waste and the further recycling of the waste through the Melissa loop. That is the first compartment. The next compartment, C2, has major purpose to liberate ammonium and nitrogen compounds, but also is a source of rhodospirillum, a potential food source, a red photoheterotroph. C3 is the nitrifying compartment, major resource target producing nitrate. And finally, C4, A and B, it is the compartment where food is produced. Microbial food, C4A, spirulines. Spirulines is a major food source, for example, in lactate. C4B, plant compartment, a major food source, deeply export and harmonized with national activity in Italy. Italy, in ESC, has decided, voilà, Melissa is of interest for us, but we want to treat ourselves and to manage ourselves the plants. Okay? At the beginning, Italy worked alone, but the collaboration is not very, very effective. C5, the consumers. But to see the effect of the consumers, we cannot use astronauts and to give the Melissa process, it is not possible. We use a model system, and this model system is rats. Rats also used for dynamic production of CO2 and oxygen. Voilà, you have here the Melissa loop, the code C1, the thermophilic anaerobic bacteria, C2, photoheterotrophy, nitrification, food production, microalgae, and higher plants. And we see also the circulation of gas. The crew produce the CO2 and receive water, food, and oxygen from the food compartments. So, and you see that's the Melissa loop. The experimental C5 co-compartment with the rats, it is an extremely airtight habitat colonized by rats, but of course rats are only receiving the gas and producing CO2. They receive their own food. Urine and fecal matters of C1 are exclusively of human origin. Organization in Israel. The Ministerial Council implementation in 2019 And so that's all what is foreseen at the level of the Ministerial Council and decided by ESA. All the steps you see here, this what it is accepted and now designed to fly at term. So scientific study found in red, system studies is auto control, and air fertilization, urine treatment, complement unit, closed-loop demonstrator, that is the MELISA pilot plant, and the plant characterization unit. That's the implementation is foreseen at the level of Ministerial Council of the ESA country up to 2024, but we are sure it will be prolongated. That's an engineering status. The main waste, fecal tank waste, paper waste treatment, formalism, one compartment. Urine treatment, nitrification, denitrification, oxygen production, food production, and we will see the different labs which are involved, look demonstration, system tools. Waste treatment, shortly, up to now, the percentage of degradation is about 70%. The volatile fatty acids, an issue that blocked us during years, is now solved. And adding to a new compartment via microbial electrolysis to show how the technology is improving. And so, see, I mentioned about it could be of interest, fiber degradation will be an additional unit, and that it was said all the degradation compartment fibers are resilient material difficult to use. It is a loss of matter. Another important, it is to know the impact of human microbiota. It was not foreseen at the beginning, but you see new topics are coming and taken into consideration. It means a major progress. It is for waste. Grow debriefing mentions a number of trash packaging. What are we doing with this trash? And we will integrate in MELISA. Preliminary degradation were performed with commercial packaging, but the degradation with these commercial products are not elaborated for thermophilic degradation. So we have to start a specific study in this respect. Compaction inhibition, and it was a special technology research program to find new biodegradable material via this program in University Ghent. That's of interest, and I was interested by your talk in this respect. The urine treatment of up to proteins. We have a preliminary set of strains identified with demonstrate efficiency up to 70%. Organic carbon could be an issue, but test and progress as planned substrate and so as to be for salinity reduction. You will see the different topics for urine. Urine nitrogen up to nitrogen gas. We observed that in space there is a major loss with a lot of nitrogen to outside. So recovery, all space vehicles are leaking nitrogen. 100 kilo per year in the ISS. Also the idea how to recover the nitrogen, but urine, unexpected, but interesting. Recovery of nitrogen from urine could lead to 6 to 7 liters nitrogen gas per day per astronaut. Process now within Melissa network, but the space engineering are still to be performed. You see the constant collaboration between scientists and engineers and programmers. Benefit, no need to add toxic compounds to stabilize the collected urine. Activity in Antwerp and Zurich. Photobioreactors successfully tested on board. 2 studies in progress and you see the involved labs. Plant characterization. Delivered many efforts were on the PCO adware developments, subsisting from plant roots and micrograins. I am interested for large contributions and we see the different topics that are of interest. You see all the labs and companies that are involved. The loop demonstration, that's important. The connection between the rats compartments or the crow compartments, nitrification compartment photobioreactor in gas phase was carried out and successful during several months. So rats could live, they have their own food, but they could receive the liquid and the gas from the Melissa loop. Integration of compartment in code progress, that's important according to schedule, a new activity, and there is also evolution to a non-facility with the participation of species with different. So, I show you what it means for the coal and the gas. You see oxygen and water to the coal, and coal produces CO2, so that is a part of the loop which is completed. And major importance. System tools. As system tools, I want to show you that we are now in state in the system tools to join engineering capacities, calculation, multiplicity of concrete approach, but also to access the all metabolomes, all the participants of the Melissa loop plants, bacteria, and aussi metabolome, c'est also proteome, genome, transcriptome. So we are in state to have a complete description at the molecular level, at the genetic level of all the components of the Melissa loop. Study, but not including effect, specific after radiation. That's the objective of the system tools, and we are in a good way to solve this terrestrial application. We use Melissa technology, for example, to recycle urine. In Roland Garros, unexpected application of Melissa. Grey water recycling, yellow water recycling postponed to 2023, but grey water recycling has worked in Roland-Garros since 3 years. Not bad. Similar Maritime new Melissa spin-off in Holland, Harmonized Mina Holding Maritime Law. No waste released to sea closer to 4 miles of the coast. Wastewater recycling on board boats and talent ship. That's my colleague from Netherlands. Pilot demonstrator for green, yellow and black waters. Objective, no release of human waste when on sea. It's a complex slide. I don't want you to tell me. The main message is above. Sanitation, social impact studies, cities as spaceships. And the use of Melissa technology in Amsterdam led to an estimated reduction of 600 tons, 1,000 tons of CO2. French Guiana, large microalgae production plant in Europe. Europe Sensulato, Guyana. Oh. And okay, the old Melissa technology has a contribution to a white paper about the circular economy. Now I want to speak on Melissa Foundation, a non-profit organization created by the Melissa to finance and harmonize Melissa PhDs and postdocs, hosting as well a POM program of PhD postdoc fellows, coordination with other Melissa-oriented PhD fellows, communication issues linked to the scientific production of the Melissa project. Pierre-Angèle Favre is the executive director and the general manager is Rob Suters, Ayat as science advisor. But what is a POM program? It's a 4 years PhD, 4 years, including that is really of a thing, an obligate year by one other partner, 3 years by one partner in one university, and the 4th year in another, by another Melissa partner. At the beginning, it was very difficult to be accepted in some universities. We used to make the whole PhD in the same place. But now it is completely accepted, and we have a lot. It is a fantastic way to integrate the young scientists in the whole Melissa community. It is becoming now a force. The POM program include also one summer school gathering all Melissa PhD fellows, and the next one is foreseen in Sofia, Bulgaria. At the beginning, it was foreseen in Varna, the Black Sea, but it was now not in Varna, but in Sofia, fully to the west, with the west of Bulgaria. So, voilà, the summer school, in 2016 it was in Catalogne, and in 2019 in Saint-Anastase in Auvergne. And I remember the very nice and fruitful discussion between the Melissa students, discussing every topic of the Melissa loop at the point. Also, I will present you most of the PhD thesis. During Pump 1, 2016, nitrogen recycling process. You gained as partner Barcelona, 3 years in Ghent, 1 year in Barcelona. a postdoc in Switzerland, and another postdoc with one patent in the Netherlands. That's for Pump 1. Pump 2. Pump 1 Napoli, impact of light of the plant growth for Luigi. Nutrient delivery water management for lettuce with Christophe Elnakel, and interesting study and simulated microgravity bacteria, Juliana Senatori. 1, 2, 3, 4 PhD and 1 postdoc. The postdoc produced 2 books about circular economy. Carles Johannes is the young specialist about the Melissa control loop, worked in Barcelona with Melissa partner Clermont for the theory of the modelization, good complementarity. Valentin Fos, Zurich, Antwerp, alkalinity, mercury nitrification. Ellen Harrison, U Cambridge and Belgian labs. And here, of interest, a PhD, Martin Bruyen in Leuven with the Clermont partner, to define the community, a very complex thermophilic community at 55 degrees, able to degrade the waste of Melissa. And we begin to have a good sight on this thermophilic community and to see that it could be stable for publication and preparation. Pump 3, just design recruited aussi the subject, curve, nutrient recovery from urine for space fishing, Zurich with as Ost University, Antwerp as partner. Next one is Jimenez, more than a great importance of phosphate. Zurich, with Napoli as partner. One thesis about the microbial electrolysis. I spoke about that to replace in the second compartment the use of et aussi microbial electrolysis solve the problem. And prediction of mass transfer, University Clermont with Barcelona as partner. It is also this description to show the continuous and necessary complementary between all the Melissa partners, and to make finally a real community of young scientists involved in the project. The topic in Napoli, and we see for the first time the Italian accepted a Melissa partner and begin to work. Mention plant rule zone characterization, effect of addition on plants with Nathalie as partner, and impact of light on plant growth, characterization and modeling is of interest because the light in the space has not the same component that the light. There is some component of the light that could be used, especially the blue light. That could be result pump 1 and pump 2, better stability of Melissa ALD due to Fourier cycles which overcome the ministerial cycle of 3 years. So it was a continuity of change and not the danger to have some gaps into programmation as we had in the past. So it will 28 publications by the young fellows, wants to know, next summer school. Bibliography of the Melissa project, also managed by us. Up to now, we have 220 publications on the Melissa topic since 1988, listed on the Melissa Foundation website. The visit of Pedro Tucuyo, former astronaut, to the Melissa Foundation in ESC. I showed this picture to show you see Christophe Lasser and all these things. All the people with whom we are, Nathalie, myself, all the people working with much. Next Melissa conference in Toulouse in November 2022. Maybe you could be interested to know about it. Main message: 2 scientific experiments are in flight implementation process. One technology modified P2, the ESS line, to see if it will be implemented in flight later. All activities approved at ministerial conference 19 are implemented. ESS team has been strongly reinforced, and the POM project ensures the continuity in scientific production and its diversity. Achievements to 21, CO2 plus urine. We could say we could use CO2 plus urine to oxygen and proteins. Demonstration of non-treated urine as fertilizer for spillings. Demonstration of treated urine as plant fertilizer. And better use of the light spectrum. Thank you for your attention.
Thank you very much, Max. Are there questions from the audience? David.
I'd like to start by thank you for the very nice presentation. So we enjoyed it. I have a question because I also represent a bit of the students that ask for how can I do to become the next Melissa case, or if they want to apply for this. I mean, the Melissa is still ongoing, or there will be new programs like Melissa where the students can apply to get projects and so on.
The next minister decision.
How can students join Melissa? How can students join Melissa? That's the question.
Talk to me, yes. Perfect.
Send me a letter. Send it to
Max.
Christophe Lasser. It could be better to inform us about the PhD project.
Okay.
And then we could put contacts with the Melissa partner who are all interested to have new students, which is really open, and also with some information with partial funding from your institution to have all these aspects, but it is clearly open.
For the
Flights, like parabolic flights or just ICSS flights? So that
The flight experiments.
Ici.
The computer.
So, which flight, the microphone is here, which flight experiments? Parabolic or?
Flight experiment, it is parabolic flights. It is just the ISS that is important to see Parabroiflex, it is finished, but it's mainly into ISS. We have a permanent permanent experiments in the ISS. And of course, integration take one aspect of ESA experiment to be developed in your own lab. But anyway, send letters to Christophe Lassard or to myself, and we'll make, or to Nathalie, and we'll make, we will relay all this information. We are really open in this respect. And we could provide partners as well.
Thank you. Are there other questions in the room? Are there questions?
Not in the chat.
No. Okay.
I have another one in case.
Thank you for your attention.
Will be also fundamental research or only applied to the compartment that the list have told before? So fundamental science can also be investigated in this project.
So the question is whether, I repeat it for the microphone, whether there is only applied research or also fundamental research involved.
Both. No restriction.
Okay.
We are open to new ideas. No material, no perspectives. It is research, it is science.
Okay. Thank you very much, Max. Thank you. And now it's my pleasure to introduce the last speaker of today, Nathalie Leijs. Nathalie studied microbiology at KU Leuven. And then, if I am not mistaken, you made a PhD at the University of Ghent in collaboration with the Flemish Institute for Technological Research on the use of microorganisms for remediation of polluted soils. Afterwards, you joined the Belgian Nuclear Research Center, SEKCN, to work with Max in the field of microbiology, and today you had not only the microbiology and genetics department, but you are very much involved also in space applications of your work, and this will be part of your subject.
Yeah.
So I give you the floor. Maybe one question. I saw in your CV that for your master's degree you worked in collaboration with Stellenbosch.
Correct.
On beer and fermented food.
Yeah.
I would have chosen wine.
It's relevant. I wanted to actually. It was an Erasmus exchange program, yeah, for my master's thesis. Okay, thank you. So thank you for inviting me, and thank you for hanging on online, but also here for all the lectures. I'm Nathalie Leijs. I'm a bioengineer by education, here. But I'm working as a scientist at the Belgian Nuclear Research Center, and where I'm also, doing space research, and that's what I would present today, if the computer allows us. Maybe you have to plug in the...
Yes, it is to just unplug and plug. Yeah.
Give that a turn. Right, one moment, please.
Yeah, okay, let's go. Yeah. So I will, Max took us already to space, and I keep you there for the next 20 minutes. So this is a picture of ISS, the International Space Station, which I think is our only destination today in space, not only for ESA, but also for people like Jeff Bezos, SpaceX, Richard Branson. This is where we should go, or where we can go. That's the only destination we have. So tourism in space, then always the question, how was your food on your holidays? So then I would say, what's the food like in space? What is it in this International Space Station? Actually, there's quite a lot. So there is really a variety of products, but also, as you see on the pictures, it's typically processed food, which is dehydrated or sterilized, heat sterilized, vacuum sealed, also canned food, because shelf life has to be as long as possible. There are some restrictions also that they cannot create crumbles, because then it floats, but actually there is really a wide variety, so it's not that bad. But fresh food is almost not. Only when there is a new docking, a cargo ship docking, then there is for a short period some fresh food, but otherwise not. So for me, that would not be my ideal vacation food taste mission. And also very important to know, it's fully dependent on Earth. So it's actually more or less like camping and filling your backpack and going to space and live off what you brought. But pack very light, because sending food to space is extremely expensive, 20,000 euros per kilogram. And that includes also the packaging, so the things which are inside is only part of it. Of course, that's what we have today, but we are in SCK also working on the future, and that's research for the future, like Max also presented. So the plans are human missions to Moon and Mars. On the Moon, the plan is the Artemis missions to put finally a female on the Moon in 2024. It's maybe a bit ambitious, that date, but that's in the strategy. And also putting people on Mars in the area of 2035. The distances, the times of these missions are totally different than what we have now on ISS, and also the isolation of what I would call lifelines from Earth is very prominent. So the scenario of food supply we have now to ISS will never be feasible for Moon or Mars missions. So then comes the question, what about this Mars food then and Mars agriculture? How are we gonna tackle that? And we need to tackle it, because food is a large volume, but also definitely drinking water. The launch costs, the further you go, are getting higher and higher, but also the launch capabilities on taking, so you never send one astronaut alone, it's always a crew of 6. Maybe to Mars, I don't know if there will be 6, but I think 3 or so. So actually also launch capabilities are really limited, so they need to take a lot of fuel to get there. So food is actually, not feasible to take it for the whole trip. Then to do agriculture on Mars, there are quite some challenges. It's not the same environment on Earth. And I put the last point because that's my area, and working at SCK-CEN, Belgian Nuclear Center, we are looking at the impact of radiation. On how can we do agriculture where we are constantly exposing everything to space radiation. So that's where these terms of indoor farming, in situ resource utilization come into play, like you see the drawings of the domes behind. So there are a lot of different scenarios. Every space agency, every new space company has its own drawing, its own scenario on how this should look like. So yeah, also the name space farming, space agriculture, space biotechnology, biospheres, you find it everywhere. But what it comes down to is this life support systems development, what Max just explained. But this does not work without fertilizers. And it's something people sometimes forget. It's very nice to draw greenhouses with plants, but where do you get your water, your fertilizers to grow it? And it doesn't make sense if that is the part you would then still ship from Earth. So the circularity, the waste program is essential. And I'm a microbiologist. Microbes are essential. This will not work with microbes. But you can't draw these nice pictures and designs with microbes. So you only see plants in these designs, but it's plants with microbes. And that's where I try to convince you. Luckily, we have these movie makers like and actors who knew it already. And they show, okay, if we want to grow plants, we need something like soil, and we need to use the own metabolic waste as fertilizers and all the bacteria in it. If you have seen the movie, you know these sections. But this is the principle, it's closing the loop. And that's exactly what it makes it finally sustainable. If you have to send fertilizers from Earth, it's not sustainable. That's the principle of Melissa, where Max gave us already the introduction, so I'm not saying anything about it. I just check the website, come to the conference, join us. There are 30 years of research, many activities going on, SEK, but other players in Belgium are active, so find the people on the website and you are definitely welcome. And I just wanted to take this stage 1 minute to thank Max, because I started 20 years ago in SEK with him and he taught me everything on space, so he's the cause why I'm here today presenting what I'm presenting. So plants in space, so a lot of different things, and you saw in the movie the potatoes. It is really one of the crops that we are looking at. You see some of the selection criteria of the crops you would want to grow, but today, and a lot of the Melissa greenhouses, and we are doing the leafy green type of developments, but today I wanted to talk about another project which is focusing on wheat, and that leads me to the Space Bakery project. Which is actually a fully Belgian, Flemish project with funding from VLAIO, the Flanders Innovation grant. So what is Space Bakery? It's exactly the same principle, that we want to combine an indoor wheat farm coupled directly to a bakery, and that all the products we use are also recycled. So some of the challenges we are tackling with this project is, first of all, the production system, so the greenhouse, the vertical farm. We also try to optimize efficient crop production and the hydroponic system, the substrates we grow on. We want to recycle the water, recycle actually also the straw, the waste of the wheat. We are paying attention to the microbial climate, which is very important in indoor farming. Also on the food production part, which is then actually using the grains and the flour to make the bread, but looking at what kind of bread could we make. And the last point is already looking for the future, because wheat is a wind pollinator, doesn't need bees, but we would like to include other crops in the future, and so we are also looking on how we can do pollination with drones and other companies. So you see all the companies and research centers contributing to that at the bottom. And I invite you, please visit the web page, spacebakery.be, to find much more info. So actually we are developing, and I don't know also if I can get that off, but it's a closed indoor farm to produce staple foods, because it's known for leafy greens. Some indoor systems exist, but once you go to something like potato, rice, or wheat, it doesn't exist really. We want to do it independent of agriculture, soil, and also climate, because it's also not what we would have in space. It's fine. Yeah. And so optimal reuse. So we are building, or actually at BrIAS, the company partner, a farm, a vertical farm with 2 containers where we are growing the crops. Then there is a bakery, and the system is set up as a clean room environment with entrances. The different contributions of all the partners. Yeah, so we have urban crops developing the vertical farm. We have Magix doing the nano drones to do pollination. We have University of Ghent developing plant sensors and models for efficient production. We at SEK, we look at substrates and nutrients we can use. We also look with Hasselt on reusing the straw by pyrolization to biochar. We analyze at SEK the microbiome of the system. We also investigate impacts of radiation, which you cannot neglect in space. And then BrIAS is looking at fermentation, baking, and also which novel products. But today, the couple slides that follow are mainly the work of SEK, of our team, and so you will get a bit more information, but on the other partners you can also find on the website some reports. So I will talk about substrates, microbiome, and radiation. Let's start the work on the research on the substrate, so on the hydroponics, the substratum, the mineral nutrients, and some on the recovery. So we looked at different substrates that we could find in space, which is actually looking at volcanic rocks, which is lava or basalt. And we also used a model which is used a lot in research in space, which is a Martian simulant, simulating regolith. We looked on how well these things are usable to do germination. And we found that some worked well, some others don't. So we continued with the lava rock system actually for Space Bakery. We don't only do germination, we developed a system that allows the plant, a wheat plant, to grow hydroponic, but to have a root support through this lava system, which worked pretty well. What else do? We look on how this lava can actually be used to release nutrients. So we made a system to do leaching, active leaching of macro and micronutrients from the rocks as a fertilizer. So what we came as a result with the setups we have is that actually from basalt and lava we can leach in our system quite well some micronutrients like potassium, calcium, magnesium. We can also get some micronutrients of iron, copper, zinc, manganese. Of course, we are missing still some like the NP and the nitrogen, phosphate, and sulfur, which are the main ones. But at least the minor ones we can actually replace by just using basalt type rocks as substrates. What we do not only work on how substrates can be used on ground, but we actually in SEK did a couple of flight experiments to ISS. So ISS is our best test laboratory to have somehow space conditions. For radiation, it's not the optimal place because it's still protected in the magnetic field, but it allows also to test aspects of microgravity or reduced gravity. So we sent these experiments. We did also algae for Melissa, but what I wanted to highlight here, so you can also Google and look that up. So we did an experiment which is called BioRock. to actually fly basalt together with microbes and look how they can still do the biofilm formation and still weather the rock or still leach the nutrients. And that was done on board ISS, so really in microgravity, but also in a system with a centrifuge simulating Martian gravity. Some papers, but the expert in the team in SEK is my colleague Rob van Hout. Then a slide on the waste. So there's a lot of from wheat. You can have, of course, the grains and make the bread, but there is a lot of the straw, the chaff, the bran, which you don't use. So there is a partner, University of Hasselt, looking how to do this, convert this via pyrolysis into biochar. Biochar is known, but the interaction with wheat and in a hydroponic system was something for us. And also the biochar is pure wheat, which is not typically what you would have. So a lot of experiments were done on the toxicity. So setups were made to include kind of biochar in wheat hydroponic systems. We found a concentration which actually helps us. So yeah, it may be not very visible, but some concentration you see is a bit higher. So it has even some plant growth promoting properties, which we are further investigating. There is still a lot of questions to be done as well. So we want to look how much the biochar can actually also help us to replace the nitrogen, the phosphorus and the sulfurous in the system. We also want to check impact on root microbiome, maybe to explain a bit this plant growth promoting behavior. But in the end, also on the grain nutrient value, because we know if you change things on nutrients, on substrates, maybe also the composition of the final grain may be changed. So that was a bit on the substrate, the work or the research on the microbiome in this system. So we know, yeah, you have microbes in the air, you have them on the leaves, you have them actually in the plant, in its roots, on its seeds, in the rhizosphere or in the substratum. So we try to monitor that and analyze it, but also try to link on some properties we follow for germination, growth, grain yield, nutritive value. Also very important is safety, so the absence of pathogens and that they don't overtake the system. So that's also for the final product safety, you have to be following this up. So yeah, we sample, it's just sampling as a microbiologist. Air, so we are running the system in an ISO 8 grade clean facility, so we keep control of the air contamination. The loads, we can keep it quite stable over the runs. But the composition, so we do also sequencing, microbiome profiling, the composition varies, and we see clearly also linked to operations, so and human activities, how often you go in, how the trays are set and things like that. So that's clearly also a source. We also following water microbiome. It's a bit the same story. The loads are quite stable, in line and kind of what you expect in hydroponics, but there are still questions on the composition. We also sequenced and followed, and we see different bacteria between the trials, but also very much linked to the growth stages of the wheat. So the wheat itself also determines what is going on. But so far we still seem to be in control of plant pathogens, but also human pathogens. So that's okay, but still research is also going on there. Then we also took the step to look at the root microbiome, and there we actually want to go towards biostimulants and maybe to engineer the system a bit and interact. So we selected microbes that are reported to interact well with wheat, but that also can survive in hydroponics and don't need soil, and that in addition have been reported in literature to interact with basaltic rocks. And those microbes we selected, and we are setting and testing currently still their effect. So different types of microbes and different setups to see whether we can actually trigger and support the growth in that way. Then a last point on radiation. Radiation on a travel to Mars can have impact on different stages. So I have some experiments in the team done on pure seed radiation. What happens if you send a bulk of seeds and you store it and you use it whenever you want it? So that's that step. So here we actually went to quite high doses. So they are not representative of a typical Martian dose, but we just want to do an accelerated lifetime test. What came out is that with the wheat varieties we are testing, actually they don't mind some radiation, and actually really high amounts of radiation. Only the highest one we tested had some inhibition, but actually that's very good news. Germination is not the only thing. You also want to check whether it still grows, and then also whether the products you get from these seeds are still okay. So that's also research that's still going on. So we test then from these first generations on wheat, the grain yield, the protein content, antioxidant content, lipid content, etc. We see no significant impact. What was a surprise is that maybe with a bit of radiation in the first generation we see more proteins in some of the grains. We are repeating that. We are also testing, not just growing them in our facilities, but in other facilities to make sure it's not a facility dependent response, but that's also part of the research. Another setup is where we actually continuously irradiate the plants throughout its whole life cycle. So it's really chronic irradiation. The point is that it's in a system in hydroponics with lava rocks, because radiation is not only happening above, but on the whole system. Again, we managed to do quite high Mars radiation simulations in our facilities without a lot of impact, so very good news. We also combined it with the biochar. Again, it seems to work out, but we are still working, of course, on nutritive values, etc. But so far, we think we can grow wheat on Mars in the system we have in mind with the radiation we would have. So these are just a few things of everything what's going on. That we have, I think, a good setup, that we can work with the basaltic rocks, with biochar, and also with the radiation. We can go forward. But what does this have to do for Earth, and why does even a company like BrIAS is interested to work with us on this research? And I think that's a very good question, and I try to answer. So the principle was here for a company producing bakery products. It's not for only the future vision of space. What they want to think about is what is the R&D or the development we need to do today to come up with the bread of the future. And then putting the flag on Mars is very concrete. You can come up with very concrete restrictions or visions for the future, and that's how they also approach this project. So they are actually looking on how in the future a company can actually limit their water use for their production of wheat, how they can minimize energy requirements, how they can actually produce crops independent of climate, season, day, night, reducing bioseeds, less surface. Also to go to more balanced products, more healthy products, so not only carbohydrates, but having breads with more proteins in, or other products like that. Also the waste stream, so the circularity is definitely something a company is also thinking about. And also for their baking technologies. If you go on Mars, you cannot make an oven there, so you have to figure out new baking technologies. So that was also a trigger for them. So space research, we believe, is doing something for Earth, and then typically on the websites, it's linked to the Sustainable Development Goals. So on food, on health, on also education. That's a slide coming up, sustainable cities and responsible consumption. So visit the website, spacebakery.be, and you find also all the partners. I also want to thank actually Serge Amey, who is retired personnel of BrIAS, but who set up many pilot plants, baking plants all over the world, but also made his own society, the Planet Mars Baking Society, and you can look it up. He is having wonderful ideas and innovation and pushing us to go further. In Belgium, we are organizing a symposium, the 7th to the 9th of June in Antwerp Expo. Everyone is welcome to join, and it's actually telling to the world what did we do for the last 2 years in this project. So it's a project of 2.5 years. So what did we achieve? What did we do? What have we still to answer maybe in the future? So all welcome, go to the website, you can register there. A last slide, so as Max also introduced, space is a multi-generation endeavor. Max started with Melissa, now it's in my hands, but there has to be someone after me because it will not be my achievement either. So we are also inviting students to work at SEK or at any of the partners on visit stages, bachelor thesis, master thesis, PhD programs. We have also a SEK Academy where you can find also some of our trainings. We used to do a space summer school, but with COVID it has not been run for 2 years, but we tried to do it again. I also want to mention Flanders Space. It's a Flemish organization, but they now, since last year, have PhD grants, Frank de Winne PhD grants. You can apply for it and with a space topic, and you can get funding for your PhD or your postdoc. So it's a new call, it's open in February, and you can apply also there. There are many other ways you can fly things. Asgard is a program to fly balloons here in KME, and you can also have a little bit higher dose on these weather balloons of radiation to test some aspects. So there are many possibilities to join. And that's just then my last slide. I'm here today telling this, but actually the work in the team is mainly done with Ali, full-time working on Space Bakery, also on Rob, my colleague, and in Nele's facilities with all the plant irradiation. And Michelle is the one for education and training in SEK. So yeah, that was my information to you, but I'm open to answer questions, of course. Yeah. Yes.
I'm very sorry.
No problem, Frank. Yeah.
Who will?
Okay. I have a bunch of questions. So
Okay.
Good. First, I ask the people in the audience if they have questions. Mark, please. Sorry. Yeah, so this Mark. I give the word to Mark. And then,
Go ahead.
Please, Mark.
It was just a comment on biochar. A friend of mine has started a company on biochar, and they use rice husks, so rice waste. And they did sort of parallel things like having to check for toxicity and stuff, and then they rolled it out and using it as a fertilizer in Cambodia and some other countries. And Southeast Asia is doing really well. So I wondered if it's unusual to use cereal waste, because obviously it started that rice. I always wondered about the potential of using wheat.
Wheat, yeah.
And she said that there was something special about rice high silica content. So rice has a higher silica deposition than other soils, than other cereals, sorry. But wheat sometimes has very high silica deposition as well, depending on the growing environment. So it was thought of it as being used for another like route for climate.
Yeah. So what is happening is that on the different trays in the container, there are sometimes different test conditions on light, and then also the waste of those are separately collected, separately paralyzed, and also the composition is checked. And there is indeed changes depending on how you grow, also on the biochar composition, and so that's also something to keep in mind in the tests you perform later on. But that's the University of Hasselt in Belgium, who is really the expert on that part. Yeah. But you are absolutely right. If you change something in your nutrient or your substrate, the rest of the chain may follow in changes. Yeah. Mm-hmm.
Then I would suggest, although the question was very long, if you can repeat a little bit the question.
Okay, yes.
So that the audience online can also follow.
Yes.
Yeah, I was wondering why you chose wheat or a cereal or a staple and not something like potato. It seems to be a bit more nutritious and doesn't rely on flowering to produce something.
Yeah. In a space context, potato is definitely on the list of crops. In this structure of this project, we had a company who is doing baking products and is really working with wheat flour, and that was their main interest. And wheat is also on the list for staple crops in space. So it's just a choice we made for this project, but it doesn't rule out potato. Yeah. In the Melissa system, in Belgium, there are potatoes in University of Ghent grown on hydroponics as well. And also there, the microbiome in the system is followed up. Yeah. Mm-hmm.
I think it's also a matter of fact that is close by the price of truffle, since it's 25,000 euro per kilogram. So a tuber might looks more like seed. Jokes apart.
Mm-hmm.
No, nowadays you can sow potatoes and then you can propagate them with steadily thereafter. So it's relatively easy to bring them into space. And then you can propagate them further.
Mm-hmm.
So you only do one flight.
It's like it, yeah. And I was thinking just in terms of most efficient crop.
In Melissa, it's potato at the moment. Yeah. Mm-hmm.
Please, from the audience and online, yes.
From me, actually. I'm interested, I think it's really, the idea of a space bakery, of course, is fantastic and exciting. I'm curious about, is the project also experimenting with different taxa, so hard wheat or bread wheat, and then also different cultivars of the subspecies, for instance? And second question, sorry,
yeah.
Does that have effect on the for your char?
I didn't say, but there is here too, which is called Apogee pedigree. It's actually dwarf varieties of wheat, which are actually developed by NASA, and we tested them as well in our setups. We didn't find them to perform so well in our setups, but dwarf conditions to have more trays is definitely an advantage. But there are other parameters you could take into account. So also the University of Ghent is testing on day-night cycles, not to go to go six day out, 6 light, 6 night. So also there you could actually look for varieties that allow that, who can do it better. So there are multiple criteria to select different cultivars and test them. But in a 2 years project, yeah, you have to do selections. But on paper, there is criteria and trade-off and things you could do, definitely. Yeah.
Thank you.
Thank you for this presentation. I was wondering, are pulses also being considered? Because I didn't see them immediately on the list. Maybe they were there, but
which was
pulses, like beans, because they have also the root nodules with the bacteria.
Yeah, yeah. There is. But not yet in this Space Bakery 1 we call, but maybe Space Bakery 2.0 or whatever. We would like to include peas, black-eyed peas, and they are part of the crops we would like to study. Exactly also to have the nitrogen fixation from air. That's something, but also to increase the protein yield in your products. So, yeah.
I have myself a question. Parameters and conditions. There are a bunch of different parameters, as you said, you can test on Earth.
Yeah.
So radiation, light, temperatures. I think there's only one question about the microgravity and the gravity condition.
Yeah.
So are you really dependent on the ISS for the testing this one? Every time do you have to go there, or there is a way that you found it in practical terms?
Yeah, and it's unfortunate that I don't have pictures, but we use simulators, microgravity simulators on ground. Yeah, and so for liquid cell cultures, we use something called RWV, rotating wall vessel, which was developed by NASA, which is actually turning your liquid against sedimentation. But for plants, we are using RPM, so random positioning machines, who are not. Bernadette is there, the wife of Max. Yeah, go. So random positioning machine is a machine where you put your plants on. It doesn't remove the gravity factor, but it turns your plant randomly, and over a certain period in time, your plant has seen the gravity factor from all sides. And that's a bit how you trick them. And we put them on those machines, and you could also include then on top of it radiation in the radiation facilities. Yeah, but we use systems in SEK to prepare ourselves for flight. Yeah, but there has been a lot of research in ISS, but also in the past on solute stations on plants growing in space.
It's available in Belgium, this, or?
The RPMs, in our labs, there are,
I will visit you.
Perfect, yeah, you're always welcome.
It's public, right?
Why not? Yeah. The systems we have are rather small, but there exist bigger ones as well in ESA, in ESTEC, where it's open facility, you can apply to run experiments there. Yeah. Okay.
Please.
Also with respect to the nutritional content of the grains that you're growing under these conditions,
yes.
Are there also effects on the micronutrients, or like what we colloquially call minerals, iron, zinc content? Is there an effect on that in these growing under space conditions?
That is a lot of the analysis on the nutritive value of the grains is still running and still ongoing. And also not all in our own lab, so we outsource that a bit, so we are still waiting on a lot of the data, to be honest. So we do seed-to-seed experiments, and we could do a couple of those in different test conditions, but it takes months, and then you collect a lot of the material, and then we are still doing a lot of the analysis. So I cannot say a lot about it, but it's something to check and to follow. Yeah. Okay, thank you for the questions. Yeah.
So, just a round of applause.
Sorry, no problem. No.
So thanks very much to our speakers, and thanks for joining us online. Tomorrow we have an event with 2 more talks of our fellows. From Philippa Ryan in the back from Kew Gardens, who will be talking about agriculture in the past in Northeast Africa, I believe Sudan and Ethiopia. And we have another speaker, Peter Scholiers, who is a food historian and will be talking to us about food culture in Belgium. So I want to give one more round of applause for our speakers. Thank you so much for joining us, and thank you all, the audience here and online, for joining us. Thank you.